as I told you, Bode plot is an extremely important graphical tool as far as frequency domain design is concerned. Our today's concern is to see what are the different ways the approximate Bode plot could be constructed, and then how to use the Bode plots for stability analysis, particularly the stability margins, the gain margin and phase margin you will be able to view on the Bode plots. So it's not just to get an alternative how to study the phase margins, but as you will see, the Bode plot will be the most important graphical tool available with us when we enter into the frequency domain discussion. I had started with it and I gave you an idea as to what are the axes. The frequency axis is on log scale, and that is why we use a semi-log paper. The vertical axis, for one plot it is magnitude in decibels, and for the other plot it is phase angle in degrees. And I told you that there are various building blocks, and if we know the Bode plot construction for the basic building blocks, after that the assembly of all those blocks, algebraic addition of all those blocks will easily give us the Bode plot, the magnitude plot as well as the phase plot. Let us get started with the basic building block. Recall what was the first building block. The first building block we had taken was the gain k. So looking at the gain k, which may appear in any transfer function, you can see that if I convert this into magnitude, the decibels corresponding to gain k is equal to 20 log k. And this remains the same for all frequencies. So naturally, on a semi-log sheet, now as I told you yesterday, when I take this axis, it is definitely for me on a semi-log paper, and on this it is dB, so it is going to be a horizontal line depending upon the gain k. You will please note that if your gain k is greater than 1, this line will come above this particular axis which you have taken. If it is less than 1, dB will become negative and your line will come below. So dB is a log of k, 20 log k. So the line coming here or here will depend upon the magnitude of k relative to unity. Phase angle, well, it remains. What is the phase angle in this particular case? 0. So 0 degrees phase angle will come. Since I have made this axis, let me tell you that our primary concern in studying the Bode plot today is regarding stability. And as you have seen that from the Nyquist stability criterion, I am more interested in 180 degrees axis, particularly minus 180 degrees, let me call it. So when I make the phase plot, please note that the axis normally taken, the vertical axis normally taken is with respect to minus 180 degrees and not with respect to 0 degrees, because this is our primary concern as far as stability analysis is concerned. So the vertical axis in the magnitude plot is going to be 0 dB, and the vertical axis in the phase plot, the origin of this is going to be, the origin of the magnitude plot is going to be 0, and the origin of the phase plot is going to be minus 180 degrees. How about this axis, please, as far as the origin is concerned? Will it be 0 radians per second? As far as this axis is concerned, I am telling you about the axis. I will repeat my point, maybe I have made some wrong statement. This is the Bode magnitude plot, the frequency on the log scale and magnitude on the linear scale. And I am telling you, for the problems we will be confronted with, 0 dB as the starting point on the vertical scale is nice. Similarly, minus 180 degrees starting point on the vertical scale will be most appropriate with respect to stability analysis. Help me please, what will be the frequency at this particular point? Shall we start at 0 radians per second or any other frequency? Please see that though omega is marked over here, it is a log scale, 0 is not defined. So in this case, this point may please be noted that since you are using the log scale, this particular frequency will start from a low value to a high value. The advantage, one of the other advantage of the Bode plot, you may please see that, you see, as a control system, you know a control system is a low pass filter. So it means you are really, as far as the useful signals are concerned, you are interested in the low frequency range as far as the analysis of the system is concerned. but you want to see the effect of high frequency noise as well. So it means in your graphical representation of the performance of a system, you are interested in both the low frequency range as well as the high frequency range, because the total system has to be seen in the low frequency range with respect to performance, in the high frequency range with respect to disturbance rejection characteristics. So if you go for a Nyquist plot, what will happen, since very high frequency is to be accommodated, the total plot in the low frequency range will get compressed, obviously because of the limitation of the graph sheet. Since the high frequency range you have to accommodate because you want to study the disturbance rejection characteristics, so you may choose a suitable scale, the low frequency region will get compressed and you may not be able to study the characteristics of the low pass filtering characteristics of the system adequately. So what will happen in the log scale, you see, the low frequency range because of the log operation will get elongated, and therefore you are able to effectively study the low frequency region as well as the high frequency region on a log scale. So this is an additional advantage of this log scale as far as control system study is concerned, because we are able to view the performance of the system over a wider range of frequency which is of interest to us. So this point may please be noted, that at this particular point, when I take minus 180 degrees as on the vertical axis, on the horizontal axis it could be, let us say for example 0.01, or if 0.01 is too low, is in that case 0.1. Why do I say 0.01 is too low? The reason being, if you see this particular graph sheet, a typical graph sheet, you find that there are 3 decades available. I will define what is a decade, multiple of 10. So you see that if you take 0.01 and you find the maximum, as you will see shortly, if 0.01 is taken, then 1, 10, 100. 100 will be the maximum which can be seen on this graph sheet, please. 0.01, this is a multiple of 10 as I am going to explain to you. So this will be 0.1, another multiple of 10, it is 1, and another multiple of 10, it is rather 10. So it means the maximum you can view in this particular case is 10 radians per second, and therefore 0.01 may turn out to be too low. You may not be able to see your high frequency range adequately. So deciding this, you see, whether it is going to be 0.01, 0.1 or even 1, it depends upon the total high frequency range you want to study. So it means this is one important point when you make up your Bode plot. The decision, appropriate decision should be taken right in the beginning. Otherwise what may happen, that you may have you may have constructed the plot halfway through, and you find that your plot is not adequate because it is not representing the total frequency range you are interested in. So this is very important, you see, marking this axis as well as the horizontal axis. Horizontal axis, first find out the total range and then take an appropriate decision. So coming back to the first building block, I find that the first building block is simple constant k, and it does not create any problem. A magnitude line, horizontal, and a 0 phase line. Go to the second building block, please. The second building block, let me take 1 over j omega. Though I told you in general it is j omega plus minus n. Let me get started with only 1 over j omega, and then I will see what happens if the value, if the type of the system increases from 1 to 2 and so on. So in this particular case, please find the phase angle picture is very clear. It is minus 90 degrees, phi equal to minus 90 degrees. So it is going to be a horizontal line for all frequencies in the phase plot. I need not plot it. Let me look at the magnitude, please. The magnitude is dB equal to 20 log omega. 20 log minus 20. Please see, dB is equal to minus 20 log omega. Now what is this log? You see, if I take omega versus dB, you find definitely that it is nonlinear function, omega versus dB. But if I take log omega versus dB, in that particular case you find that you have got an equation of a straight line with a slope of minus 20 dB per unit of log omega. I need your attention, please. Minus 20 dBs per unit of log omega. Okay. This, now as I told you yesterday, that it is this contribution from Bode which converts, which makes the construction of the frequency response plots very simple. This total plot becomes simply a straight line of minus 20 dBs per unit of log omega. Now what is a unit of log omega? You know that unit of log omega will come by log 10, factor of 10 is equal to 1 it gives you, and therefore log omega 2 by omega 1 is equal to unity gives you omega 2 equal to 10 omega 1. So it means when the frequency changes by a factor of 10, what you have 1 unit of log omega. This I am telling you because what we have, are going to have this particular semi log paper in which the factor of 10 is available to me. Okay. This is the factor of 10, 1, 10, 100, 1000 and so on. So it means this is a unit as far as log omega is concerned, and you find if it is visible, hopefully it should be visible, then after a unit of log omega you find there is a change in color on the semi log paper. So if you change the frequency by a factor of 10, it means on a log scale you are changing it by a unit of log omega, and this is referred to as a decade of frequencies. So it means I can say that if I am using a semi log paper, in that particular case dB equal to minus 20 log omega is a line, is a straight line with a slope minus 20 dBs per decade of frequencies. Now let me say how do I make this sketch. Magnitude sketch I want to make, the angle sketch is very simple, it is minus 90 degrees. So this is omega. Now please see, semi log paper I am referring to now, and this is a dB. So minus 20 dBs, you see that one thing, what is the frequency range of interest? Please see, your factor is 1 over j omega. You find that this particular factor is going to contribute for all frequencies. It is significant for all frequencies, right from very low frequencies omega is equal to 0 to very high frequencies. So it means this particular factor, I am interested in the overall ranges of frequencies. Let me say that this is 0.1 or any value you may take. What is a decade? Decade is 1 over here, and what is minus 20 dBs per decade? So let me take minus 20 dBs here, let us say 10, minus 10, minus 20 dBs. Let me pass a line through here. This is a line of minus 20 dBs per decade. So it means I have to take a decade of frequencies, and after at this decade put it down by minus 20 dBs, join this to this particular point, you have a line of minus 20 dBs per decade. Yes, 1 over j omega, not j omega, because it is minus 20 dBs per decade I am taking. After a decade of frequency, the magnitude goes down by minus 20 dBs. You see that we have a line now, this line is effective in the entire region. Up or down, why it should be shifted up means that it is going to be effective for frequencies lower than 0.1 as well.
So at 0 it should be 20.
Yes. There is no 0, one thing.
Sorry,
at 0.1, then if you are taking, it is equivalently speaking, if you have a paper here, then you take a decade of frequencies here and just take 20 here. It depends, you want on the semi log paper a decade. If you start from here, so how do you take 20 in that particular case? To take 20 you need a decade of frequencies. After a decade you take it 20 this way or minus 20 this way, it is the same line, a line of minus 20 dBs per decade. Or equivalently speaking, in this case you have to take that this particular line, you can equivalently take it this way, dB equal to minus 20 dBs per decade or minus 20 log omega. I want a starting point, please see. Help me, what is the value? At omega is equal to 1, this is the line I have given you. As far as minus 20 dBs per decade is concerned, as he suggested that, let me take this point and take it 20 up. That way, as far as the line is concerned, you take any point on this axis, you mark a decade on this side, you take it minus 20 dB down. You mark a decade on this side, you take it 20 dB up. It is going to be a line of minus 20 dBs per decade. But you see, you have to tell me the plot of 1 over j omega, from which point will this line pass? That is very necessary. As far as drawing the line of minus 20 dBs per decade, that is simple. Yes, omega equal to 1, this is what I was going to see. Now you see that first is drawing a line of minus 20 dBs per decade. You have to be very clear that this is your a particular starting point. If you are taking higher frequencies, you go minus 20 dB down. If you are taking lower frequencies, you go plus 20, that is 20 dBs up. This is equivalent. Your line will be minus 20 dBs per decade. Now from where will it pass? Just see, at omega is equal to 1, dB is equal to 0. So it means you actually now will do the following. Whatever may be your frequency scale, let me take it is 0.01 here, it is 0.1 here, it is 1 here, and it is 10 here. Let me say this is the frequency scale I have taken. Now at omega is equal to 1, it is minus 20 dBs per decade. So it means you will have to now take the line passing through this point. And since you have to draw the line passing through this point, why to make it pass through the origin and then take parallel? You can straight away draw a line which passes through this point and has a slope of minus 20 dBs per decade. You will go to 0.1 and take it plus 20 here and let it pass through here. Okay? You will go to 0.1 and let it pass through here. Equivalently, you see that you in this particular case, this is good enough. This will be the right point. This will be the right strategy, that you take the point omega is equal to 1 and from that point let the line of minus 20 dBs per decade directly pass, and that you can take by going 1 decade down, and with respect to this you take plus 20 dBs up. Okay? So now you help me please, let me retain this particular plot. Help me now, what is 1 over j omega squared? 1 over j omega squared identically. Now it is going to be dB equal to, or let me just change the color so that you know that a different situation is being discussed now. Minus 40 dBs per decade. Exactly same thing now, because your magnitude is going to be dB equal to minus 40 log omega. Again you will pass it through omega is equal to 1. So it is going to be now a line of minus 40 dBs per decade, and let me tentatively take this line. And similar is the situation if you take this to be in the numerator. Numerators normally we do not come across, so let me not make the issue complex. But you see, as far as the Bode plot construction is concerned, the slope will change, that is all. Instead of minus 20 dBs per decade, it will become plus 20 dBs per decade, that is the slope will become this way, or plus 40 dBs per decade as the case may be. Okay? Now let me mix up the two and let me say that I have a Gs equal to k over s or k over s squared. In this particular case, please see, one aspect is this, that you plot for k, you plot for 1 by s and add up the two. But you see that this k by s factor could be taken as a single building block. It works better, it works quicker. As far as the phase angle is concerned, there is no problem, it is again minus 90 degrees. Let us see the magnitude. G j omega is equal to k over j omega. So dB, as you see in this particular case, is minus 20 log omega plus 20 log k. So it simply shifts your point, you see. Now again, this is a line of minus 20 dBs per decade. You can see that, you can put it this way, y is equal to mx plus c. The only thing is that now constant has changed. In your standard straight line equation with log omega is equal to x, it is log y is equal to mx plus c. So it is again minus 20 dBs per decade. Only thing is this, that the point from which this line is to pass is shifted. So it is better to plot it directly this way instead of adding the two plots. Help me, where is the point? So what is the point? You take omega is equal to 1, you find that your dB is equal to 20 log k. So it means one point is this, that if I take this axis, omega is equal to 1, 20 log k magnitude you take. It can be down or up depending upon the value of k, whether k is greater than 1 or less than 1. Now this is the point from where the line of minus 20 dBs per decade should pass. So I will suggest that you go this way, it depends how if you are comfortable with drawing a parallel line, fine, otherwise you take a point. take a point correspondingly at the location with the same dB 1 decade below and make it 20 dBs up and let it pass through this point. You see that you can take a corresponding point with the same magnitude on the other side and then take it 20 dBs up. So, in that particular case you find that from this particular point, if you make a line, in that case minus 20 dBs line per decade line could be drawn. Equivalently, you see that if you take omega is equal to k, you find that dB is equal to 0. So, it means your line has to cut this horizontal axis at omega is equal to k. I leave it to you, you see what method you are more comfortable with. Either you locate this particular point and pass a line through this, or you take omega is equal to k point on this axis and pass a line of minus 20 dBs per decade through this. Okay? Now, a question please, let me change a color here, k by j omega squared, can you help me? This is okay, that it will be minus 40 dBs per decade. I am sure you know it, but help me about the point through which it pass. The point through which it pass. You can write this equation, basic equation you should write. The basic equation is dB equal to minus 40 log omega plus 20 log k. Yes, please see that this is the point, it needs your attention please. If you identically you increase it, you see your equation is now dB is equal to minus 40 log omega plus 20 log k. So, either you take omega is equal to k, there is no problem. No, omega is, no, it will be the same thing will be applicable there as well. Omega is equal to k under root. If you take, in that particular case you can pass it through this particular point, or if you take omega is equal to 1 rather, then it will remain the same, because 20 log k is the point through which the line of minus 40 dBs per decade will pass. So, it means either you take omega is equal to 1, locate the point 20 log k, and now the line is minus 40 dBs per decade, or omega is equal to under root k as has been told, and your line should pass through that point. I hope it is clear, and it may increase to 3, 4, 5, but I told you normally we come across type 0, type 1 and type 2 system. And interestingly, I think let me make a mention here itself, the Bode plot if I give you, you see if you are working with a type 0 system, in the low frequency range you will find you get a horizontal line. It will simply mean that there was only a constant k and j omega was missing, it is j omega to the power of 0. If in the low frequency region you get a line of minus 20 dBs per decade, as you will see other factors will add up in the high frequency region, as I will convince you that the other factors of the transfer function will add up in the high frequency region. So, interestingly the Bode plot, just the very site of the plot, the magnitude side of it tells you that whether you are handling a type 0 system, a type 1 system or a type 2 system. A 0 dBs per decade line, a minus 20 dBs per decade line or a minus 40 dBs per decade line in the low frequency region tells us whether the system under consideration. Maybe the transfer function model is not given to you, but still you can tell me which type of system you are handling, you are analyzing. Okay. Let me go now quickly go to the other building blocks. With this introduction, I think the speed can be increased now. Gs is equal to 1 over 1 plus j omega t, a pole, a simple pole or a simple lag I can call it. Okay. By simple I mean a first order, I will make it quadratic when it is a second order factor. Okay. Now, here you see that as far as the magnitude is concerned, this can be written as 1 over 1 plus omega square t square under root angle minus tangent inverse omega t. Let us first look at the magnitude. dB equal to what please? dB in this particular case you find is 10 with a minus sign log 1 plus omega square t square. I think now some of the simple derivations I like to miss, so that I can conclude the discussion on Bode plots today, but those derivations I will give the guidelines will be very simple. This is your plot without any approximation please. It is dB is equal to minus 10 log 1 plus omega square t square. I hope this is well taken. Come on, now you divide this into two frequency ranges. I take a frequency range, let us say that this is the point where omega is equal to 1 over t. Okay? Now, when omega t is less than 1, that is you are working in this particular range, because this can be neglected. If omega t is less than 1, this can be neglected, and the other is omega t is greater than 1. In that particular case, 1 can be neglected, and this is my frequency range. I want you to give me a sketch for these two cases. Omega t is much less than 1 and omega t is much greater than 1. Now, when omega t is much less than 1, you find it is a 0 dB line. There is no problem here. But let me go to omega t much greater than 1. I like to write this equation again. dB is equal, so that you know that what this is the exact equation. And case 1, omega t is less than 1, in that case dB is equal to 0 is your equation. Case 2, omega t is greater than 1, dB equal to minus 20 log omega t is your equation. You can see dB is equal to minus 20 log omega t. So, you see that for omega t greater than 1, and this is a straight line now, omega for various values of omega, if I take omega versus omega t, this is a straight line of minus 20 dBs per decade, okay, for the frequencies under consideration. And what will happen at omega t is equal to 1? At omega t is equal to 1, it passes through dBs is equal to 0. So, it means this equation passes through 0 dB line if I extend it to omega t is equal to 1, but otherwise in the large frequency range it is a range of minus 20 dBs per decade of frequencies. So, it means if I make a sketch of this, this is omega equal to 1 over t or omega t is equal to 1, this let me call it as my corner frequency. This is the corner frequency. So, at the corner frequency you just take the two ranges, one range you take on this side and the other range you take on this side. So, if I extend these ranges, then in this particular range the plot is this. If I just assume that this approximation is valid up to omega is equal to 1 over t, okay, in that case it gets extended to this point. And if I assume for this range this approximation is valid again up to omega is equal to 1 over t, in that particular case my line of minus 20 dBs per decade passes through this particular point omega is equal to 1 over t. Okay. So, I get now this as the total plot, omega is equal to 1 over t as my corner frequency, and this is the equation I am getting. Now, help me please, what is the phase angle plot? Please make a sketch.
Isn't it derived from the actual plot?
Yes, that we are going to see. What is the actual plot and what is the amount of deviation, I am going to see this, but help me please in this particular case, what is the corresponding phase plot, and let me see what are the next building block appropriately I should take. Help me about the corresponding phase plot please.
Sir, is the exact slope minus 20 dB per decade there?
Yes, let us see how you can see, and even the actual plot construction also let me see now. Please see, as he said, what is the deviation with respect to the actual plot? dB equal to minus 10 log 1 plus omega squared t squared is the actual value. Okay. Now, this actual value you just store it, and case 1 dB equal to 0, case 2 I am writing in the form dB is equal to minus 20 log omega minus 20 log t. I am writing this as the second equation. For omega t greater than 1, my equation is dB is equal to minus 20 log omega minus 20 log t. Now, you can see, you just give me a sketch of this line, it is y is equal to mx plus c. It passes through the point omega is equal to 1 over t, because dB will be 0, and the line is a minus 20 dBs per decade. I hope you are getting my point. Assuming that the approximation is valid up to the point omega is equal to 1 over t. In that particular case, this line is an accurate approximation, otherwise there is an error between this and this. What I have to do is, I have now to calculate the error between the 2 points, between the actual point and this curve. This point may please be noted that if the approximation is valid in this particular case up to omega is equal to 1 over t, you have this line. if in this particular case the approximation is valid up to omega is equal to 1 over t, you have this line. So, these two independently are accurate plots provided the approximations are valid. Now, yes.
So what do you mean by valid? Because actually at omega t is equal to 1, it should be minus 3 dB.
Yes. Now, since they are not valid, I have to calculate the error. As he has pointed out, if I calculate the actual plot, you see, just take various values of omegas and make an actual plot of this. The actual plot of this turns out to be this. I am making a rough approximation. So, the green one is an actual one plotted from here, and this red one is from here, and this red one is from here. This is approximation extended up to omega is equal to 1 over t. This is an approximation extended again up to 1 over omega is equal to 1 over t. Now, the question is this: if I have to make this particular green plot by using the calculations from this particular equation, then the advantage of the Bode construction is lost. The power of the method is this, that if you give me the error at one or two crucial points between the green and the red plots, I will be able to construct an approximate green plot which will be quite close to the one can obtain using this particular equation. And the answer has already been given by one of you, that if you do the calculations at this particular point at omega is equal to 1 over t, this gives you minus 3 dB. You can do this calculation please. At omega is equal to 1 over t, it is going to be minus 10 log 2, and minus 10 log 2 is 3, minus 3. So, it means at this particular corner frequency, as I have named it, the actual value is 3 dB down. You see, what normally is done this, that couple of more points are taken, and the normal practice is this, that the one point which is taken here is at a frequency which is half of this frequency. So, if this is omega is equal to 1 over t, I take omega is equal to 1 over 2 t here. It is a normal practice. You can take it more than that, you can take it less than that. And another point which is normally taken is 2 times this frequency, which I take 2 by t here. Okay. So, if you put omega is equal to 1 by 2 t and calculate what will the error? The error will be between this and this. You will find this error turns out to be minus 1 dB. You can please check. Put omega is equal to 1 by 2t and take the difference between this and this. The error is minus 1 dB. You put the value omega is equal to 2 by t and take the error between this plot, this value and this value. Now, you will find again the error is minus 1 dB approximately. So, at frequencies 1 by 2t and a frequency 2 by t, the errors are minus 1 dB here and minus 1 dB here, and these 3 points are found quite adequate to make the green plot, that is to make the correct plot, the accurate plot for this particular system, which takes care of the approximations. And this frequency omega 2 by omega 1 is equal to 2, a factor of 2 on this side or a factor of 2 on the other side is referred to as an octave of frequency. Like a decade is a factor of 10, an octave is a factor of 2. Okay. Now, I sum up and wait for your questions please. I sum up now. The factor Gs is equal to 1 over 1 plus j omega t. This is my factor, and the method is the following: magnitude plot. I take omega is equal to 1 over t as the corner frequency, okay, and I make this line and this line a line of minus 20 dBs per decade. You will please note one point, that if you calculate this at omega is equal to 2 by t, this will turn out to be minus 6 dB please, this magnitude, and hence minus 20 dBs per decade is same as minus 6 dBs per octave. This may be helpful in case the graph paper is not available for a decade. One octave on the other side also you can take to make a line of minus 20 dBs per decade. Minus 6 dBs per octave and minus 20 dBs per decade are identical, they are same. So you see that you make this is your corner frequency, and this is called asymptotic Bode plot, please. Now from the asymptotic Bode plot, the actual plot will come in the following way. Just mark a point 3 dB down. Take 1 octave below, mark a point 1 dB down. Take 1 octave above, mark a point 1 dB down, and join these, making asymptotic to the 0 dB line and asymptotic to minus 20 dBs per decade line. This becomes your accurate Bode plot without any calculations.
So how does minus 6 dB come, sir?
Minus 3 dB comes, actual value is dB is equal to minus 10 log of 1 plus omega square t square. This is the actual value for corresponding to the green curve. An approximate value we have taken 0, dB is equal to 0. So this omega is equal to 1 over t gives you 3 dB, minus 3 dB, that's all. And identically for omega, this is the simple calculation at omega is equal to 1 by 2t or omega is equal to 2 by t, and subtracting it from the asymptotic value. Okay, so this way we get the green curve. Now look at the zeros. Yes, zeros we do come across. GS is equal to 1 plus j omega t. Now 1 over j omega t if I take, please help me. Now I think I have to speed up with this introduction. 1 by t is there. So it is going to be this as the asymptotic plot. This is your line minus 6 dBs per octave or minus 20 dBs per decade.
Plus.
Now you can check, the errors are going to be plus. You take 3 dB up, you take 1 dB up at 1 octave below the corner frequency, you take 1 dB up at 1 octave above the corner frequency, make a line asymptotic to the two, you get this particular thing. Okay, I hope you are getting my point. Now I can just keep on extending the cases. 1 over 1 plus j omega t squared, a double pole. Come on please, orally I think we need not even draw. It is minus 40 dBs per decade as the line at the corner frequency omega is equal to 1 over t. Note the word corner frequency, it is omega is equal to 1 over t when your factor is in the pole in the time constant form. Okay, 1 plus j omega t is the form of the factor we have taken. Now minus 40 dBs per decade, and how about the errors? Please see that the errors will get algebraically added up. Minus 6 dB at the corner frequency, minus 2 dB at 1 octave below and above the corner frequency. Okay, I am left with couple of more. Oh yes, angle for this please. Angle for this I have to take g j omega equal to 1 over 1 plus j omega t. Now please see that if you see different books, as far as the angle plot is concerned, different methods will be given. At least 5-7 different methods you will be able to get. Different methods means actually different approximations. What I feel is the following: angle of g j omega equal to minus tangent inverse omega t. And if I make a sketch, omega is equal to 0 gives me 0 and omega is equal to infinity gives me minus 90 degrees. And at omega is equal to 1 by t, I get minus 45 degrees. So you see that the angle plot is the following, please. Skew symmetric with respect to the corner frequency, this is tangential function. Now I say that many books will give different methods. You see that they approximate it by one, that you make a template and keep on using it, you want to avoid calculations. The other, well, you just approximate it, omega is equal to 1 by t is here. Go 1 decade below, so it is omega is equal to 1 by 10t, draw a vertical line. Go 1 decade above, omega is equal to 10 by t, draw a vertical line. Join these two lines, passing through this point. This red straight line may be taken as the asymptotic approximation of the angle plot. So that way you see, if you are getting a factor of double pole, in that case it will become 0, minus 90, minus 180 degrees. So this will be a straight line passing through minus 90 degrees line and at omega is equal to 1 over t. So 1 decade below, 1 decade above, join these 2 points, it is a reasonably correct approximation. But this approximation can give you an error to the tune of 6 degrees, and 6 degrees error in phase margin calculations is an appreciable error, and fortunately the calculations of this factor minus tangent inverse omega t is not that clumsy. You see, after all, you have to simply press the calculator buttons if you are not sitting on the computer, assuming that you are really not. If you are sitting on the computer terminals, then no approximation is involved. We are assuming that it is a paper and pencil design, and with it also the calculator can be added to the tools, and if that is the case, probably the angle calculations is not very difficult and all the angles get added up. So my submission, my viewpoint is this, that the approximation in the angle plot should not be made. Okay? Otherwise, yes, it is a straight line approximation, and keep on adding up the various straight lines for various plots because the angles are getting added, and a suitable asymptotic approximation, a suitable straight line approximation for the angle plot also you will get. Okay? But I think you can avoid that. Now, looking at the one more factor is there, and that factor is GSHS or only GS is equal to 1 over omega n squared s squared plus 2 zeta omega n s plus 1. This is one more factor. Please see, before I go to this factor, I will give you the idea how to take up the phase margin and gain margin on the Bode plot, because even if I do not get time for this, I will tell you to study of your own, but gain margin, phase margin idea I have to give. Please help me. If I take a typical, okay, let me take a, I will come back to this. So, let me retain this. If I get time, I will come back to this. Take a typical function Gs is equal to k over s into 1 plus st1 1 plus st2. Please make a sketch of this, the magnitude plot. The magnitude plot in this case, you will help me please. How do I get started? You please see that omega 1 is low frequency plot. Let me first take omega is equal to 10, k is equal to 10 typically. Let me take k is equal to 10. So, 10 by j omega is one factor, and this is going to give you a line of minus 20 dBs per decade passing through omega is equal to 10 or an appropriate magnitude over here corresponding to omega is equal to 1. Take the next corner frequency please. Now, please see that this plot is valid for the entire frequency range. Now, you can take 1 over 1 plus st1. What is the plot of this? Assuming that omega is equal to 1 t1 lies over here. You see, in this particular case, let me change the color over here. This is your plot as far as omega is equal to 1 t1 is concerned, as far as this pole is concerned. Now, if you add up these two plots, please note that it is equivalent to changing the slope of the original line, which was otherwise valid for the entire frequency range, changing the slope of this original line at the corner frequency by a factor of minus 20 dBs per decade. So, this original line was earlier minus 20 dBs per decade. From this corner frequency, the slope changes by another minus 20 dBs per decade. So, at this particular corner frequency, you change the slope by minus 20. So, it total becomes minus 40, and hence the addition of the two is a line of minus 40 dBs per decade passing through the corner frequency taken on this particular line. Same argument is valid for the third case. Let us say omega is equal to 1 by T2 is lying here. Omega is equal to 1 by T2, and this is the minus 20 dBs per decade plot. Now, if you add up these three, it is equal. You see, after all, up to this point, it does not add up anything. It is a 0 dB line as far as asymptotic plot is concerned. So, it means what I have to do is, I have to take this particular point on this line and add up the slope by another minus 20 dBs per decade. So, it becomes minus 60 dBs per decade, and this becomes my line, and hence this becomes the total magnitude plot for this particular system, asymptotic. So, I am now, you see that procedure will be define the corner frequencies, and at each corner frequency keep on changing the slope by a factor of minus 20 dB if the pole is in the denominator, plus 20 dBs if the pole is in the, if the factor is in the numerator, because the numerator one is a 0 which contributes a slope of plus 20 dBs per decade. Now, how about the approximations? The approximations can be made like, the corrections can be made like this. Take the corner frequency, take a point 3 dB down. Why down? Because the slope changed by minus 20 dBs. If there was a change in the slope by plus 20 dBs, I would have taken this 3 dB up. So in this case it changes by minus 20 dBs. Now it is not the slope at this particular line, but whether this error will be up or down depends upon the net change at the corner frequency, whether it is with a negative sign or with a positive sign. In this particular case it is with a negative sign, so I take it down, and here 1 dB, 1 octave below is here and 1 octave above is here. Note interestingly, so if I take now another point, it is 3 dB down here. 1 octave above, okay, is here, 1 octave below is here, 1 octave below could be here also, does not matter, it is just the algebraic addition. Does not mean that 1 octave below cannot cross this particular point, or it cannot be at the same point. It can be, if it is at the same point, it becomes 2 dB down. Please see that it is just an algebraic addition. 1 octave above, because of this factor has come over here, 1 octave below because of this factor can come at the same point. In that particular case, net error at this particular point will become minus 2 dBs, and hence a plot passing through suitably all through these points is the accurate plot of the system. Okay, help me please, what is the gain crossover frequency? Now recall the Nyquist plot. Nyquist plot for this particular system, yes, it will be this way, isn't it? For this particular system the Nyquist plot is going to take this shape. The frequency at which the magnitude is 1, we have said that it is our gain crossover frequency. So naturally the green line intersecting this particular point is your gain crossover frequency. Now you said that the phase angle with respect to this minus 180 degrees line is your phase margin. Can I say, you see, looking at the time, I don't want to draw a fresh graph, but I hope you will not get confused with this. If I draw a Bode plot right here, this is minus 180 degrees line, I am now making a phase angle plot. Phase angle plot in this particular case, please help me, what is the total frequency angle range? Can I say that it will be minus 90 to minus 270? Is it visible? I think it's visible from here also, minus 90 to minus 270 from the polar plot. Otherwise you can say that for omega tending to 0 it is minus 90, for omega tending to infinity it is minus 270, it is very clear from here. So it means I expect the plot, this is minus 90, this is minus 270, I expect the magnitude, the phase angle plot to be of this nature. Asymptotic to minus 90 line on this side, asymptotic to minus 270 line on this side. Okay, and this is visible from here also. Can you tell me please what is the phase margin? Can I say that this is the phase margin? Because this is the angle which can be added to the system to make the phase angle minus 180 degrees. So this becomes the phase margin of the system. Please see. So phase plot I am saying, the phase plot in this particular case, phase angle phi minus 90 degrees minus tangent inverse omega t1 tau 1 minus tangent inverse omega tau 2. Let omega go to 0, it is minus 90 degrees. Let omega go to infinity, it is minus 270 degrees. So I have an entire range of frequencies. So in the lower range of frequencies it becomes tangential to minus. I don't have omega is equal to 0. So I am going to make it tangential to minus 90 line. And in higher frequency range I am going to make it tangential to minus 270 degrees line. This is my vertical axis as far as the phase angle plot is concerned. And what are the different points here? I am saying that you calculate instead of taking the straight line asymptotes, because they are going to give you a lot of errors. So you make couple of calculations in between and draw a rough plot that gives you the phase angle plot. And at the gain crossover frequency, if I calculate the phase angle, I say that this is the phase margin. And this If you take it this way, it is a positive phase margin. If you take it this way, it is the negative phase margin, because this much of angle can be added to make it minus 180 degrees. So this is the phase margin on this particular axis, which you have to now take with respect to minus 180 line. That is why the importance I told you, when you take the phase angle plot, you make your plot with respect to minus 180 degrees line. Can you now tell me what is the phase crossover frequency? This will become the phase crossover frequency, the frequency at which the angle becomes minus 180 degrees. This is the corresponding point here. Help me how to get the gain margin. What is this? This is 1 by A effect. 1 by A makes it unity, and unit here means 0 dB. 20 log 1 is equal to 0. So if I take this vertical line, please see that this much is the gain margin. This much of gain I can add to this system. This much of gain I can add. This much of dB is the gain margin. This much of gain I can add to this system before the system becomes unstable, or before at this particular angle. This angle will be minus, you see, this angle will be minus 180 degrees, magnitude will be 0 dBs. It means it is equivalent to that the Nyquist plot passes through the minus 1 plus j 0 point. So intersection of this you have to take, this much of dB you have to take, this gives you the gain margin, and this gives you the phase margin. And the plot of this type of vector, please do read. I will be taking up a numerical example in the tutorial class so that this gets covered, and we start with a new topic next time. Thank you.